All right, so here's your lesson for 3.5 multiple angle identities. Very much like the previous lesson with the sum and difference identities, we have these formulas here that we're going to use, and we're going to use them along with the unit circle or perhaps some arbitrary triangles, to either prove identities or solve, okay? So let's jump right into it, proving an identity. So here's why or where the double angle identity comes from, at least for sine. It's an easier one to prove. Okay, we would all agree here that the sine of 2u, okay, could be written as the sine of u plus u, right? And we just did the sum identity for sine. Okay, what's the sum identity for sine? So we'd have sine of u, cosine of u. Okay, we'd be adding that to the cosine of u, sine of u. All right, and anytime you're adding two of the same thing, right, then you just get two of that thing. So 2 sine u times cosine u, which is what they wanted us to prove. Okay, so it's just a shorthand version of the sum identity, okay, for the double angle identity for sine. All right, over here, trying to prove, excuse me, that this would be equal to the cosine of 2 theta. Okay, well, what we have here is a factoring pattern from algebra called the difference of squares, meaning that we could write this as the two items being squared, right? So we would have cosine squared theta squared, right, minus sine squared theta squared. Okay, so I'm just rewriting what I already have. Anytime I have the difference of two things being squared, I can factor them into two binomials, one with addition and one with subtraction. So that would look like this. I would have cosine squared theta plus sine squared theta. Alarm should be going off right now. And then I'd be multiplying that by cosine squared theta minus sine squared theta. Okay. What alarm should be going off? Well, this is the Pythagorean identity, right? Cosine squared plus sine squared equals 1. Okay, and then cosine squared minus sine squared actually ends up being the identity for cosine of 2 theta. Okay, cosine of 2 theta equals cosine squared minus sine squared. All right. Okay, so how do we go about applying some of these? Again, it could be to an arbitrary triangle like the one at the right here, okay? We'd want to find the hypotenuse, though. It could come in handy as we're going. So 4 squared, right, plus 1 squared has to equal c squared. Okay, so what is that? 16 plus 1 is 17. So that means c would be root 17. That's really messy. That stinks. Okay, told you quizzes and tests probably won't give you something that messy. All right. But then we're going to use the formulas for each of these to be able to simplify this the best that we can, okay? So let's see here. Sine of 2 theta, you're using the identity at the top of the page for this. This is equal to 2 sine theta cosine theta. All right, so I'm going to reference my triangle then. And the sine of my triangle, opposite over hypotenuse, is 1 over root 17. So I would have 2 times 1 over root 17. The cosine would be 4 adjacent over root 17. Okay, and when I simplify this, okay, numerators get multiplied together. So 2 times 1 times 4 makes 8. Root 17 times itself makes just plain 17 because the square roots would cancel out. So my best answer would be 8/17. Worked out to be kind of nice. Okay, so now when you do the cosine of 2 theta, notice that you do have a couple formulas here for this. Okay, so really it's up to you which one you choose. Okay, we could prove that any of these work. Okay, for the double angle for cosine. Right, I'll probably just use the original one up there of cosine squared minus sine squared. They would all give us the same answer, obviously. So this equals cosine squared theta minus sine squared theta. All right, again, I'm going to be using that triangle there. Okay, so the cosine of theta is adjacent over hypotenuse, so 4 over root 17 squared. And then the sine is going to be 1 over root 17 squared. Okay, and when I square each of those, I'll end up getting 16/17 minus 1/17. All right, and actually works out kind of nicely. I end up with 15/17 as my best answer. Okay, and the last one there is tangent of 2 theta. Go up here to the double angle for tangent. Okay, you only get one option, 2 tangent over 1 minus tangent squared. Okay, so let's go back down there, 2 tangent over 1 minus tangent squared. Okay, and in this case, tangent is going to be 1/4, opposite over adjacent. So I end up with 2 times 1/4 on top in the numerator, and then 1 minus 1/4 squared in the denominator. Okay, so 2 times 1/4 on top is 1/2. Okay, and then 1 minus, what, 1/16 on the bottom. All right, so some messy algebra here to get this fixed up, but I would just make that 1/16/16. All right, so when I subtract, I would end up with 15/16. So this equals 1/2 divided by 15/16. All right, but we never want to divide by fractions, right? We always want to multiply by reciprocals. So we'll multiply this by 16 over 15. Okay, and when we do that, the 2 and the 16 cancel to a 1 and an 8. So I think 8/15 ends up being our best answer. Okay. The half angle identities are much of the same, right? We're just using the formulas that are pictured above. All right, the tricky part here is when we do u divided by 2 equals 165, we're trying to think of what that half angle is. In this case, it's 330 degrees. Okay, so whatever double that is. So that means we're referencing the unit circle here in this example. Okay, now if we were referencing a triangle, that'd be a little different. But in this case, it's a unit circle. So we want to look at 330 as our reference point when we plug into each of these formulas. All right. Not sure I'm going to work through all 3 of these with you. I think you could probably handle plugging into a formula. But I'll show you one of them here. So the sine, half angle identity for sine. Okay. Just paste that down there for us. And again, nothing you have to have memorized here. All right, so we will need cosine then, all right, from the unit circle for this. Okay, so what is the cosine of 330? That's what we should be thinking about right now. All right, lucky us, it's 1/2. Okay. So I'm going to plug that into this formula. I have plus or minus the square root of 1 minus 1/2 all over 2. Okay, now if you had a radical inside the radical with the root 3 over 2 or root 2 over 2, things could get a little dicey. It typically ends up being a point where we just can't simplify any further, and it is what it is. All right, but in this case, we can simplify this 1/2 minus, or 1 minus 1/2 is 1/2. 1/2 divided by 2 is 1/4. So we actually end up getting, see, I'll just write that out just so everybody can see it. So that's 1/2 over 2, all right, which equals the square root of 1/4. All right, now we can simplify some of this, okay? So this actually does equal square root of 1 over the square root of 4, okay? Or you could look at it as a whole square root as well, all right? And we end up actually getting 1/2 for our answer here, plus or minus. Okay, so it's a little bit of a unique one in that sense. They don't always work out that nicely. Okay, and again, cosine and tangent half angle identities are the same. Okay, notice that the formulas change just a little bit. All right. Okay, reducing the power of 4. We're not going to get into that. Solve algebraically. You know, this would be one where you would have. This is actually 3/6. There's a good lead into that where we would use a formula, all right, what it says equal to, and then we would solve it from there as if it was an equation, right? So like the cosine of 2x, you know, we would end up with, if we used a formula for that, what is it? Cosine squared of x minus sine squared of x equals 1/2. Okay, we'd have to try to solve that. That'd be a little tricky there. I would probably try to get everything in terms of cosines. So if I was doing this, I would probably replace one of these, like the sine, with 1 minus cosine squared. All right, so I would have cosine squared x minus 1 plus cosine squared of x equals 1/2. Okay, and then if I combine like terms, I would have 2 cosine squared of x minus 1 equals 1/2. All right, and now I'm solving it like an equation, right? I'm going to add 1 to both sides. Okay, so I have 2 cosine squared of x equals 1.5. All right, or 3/2 or whatever you want to call it. Divide by 2, divide by 2. So I get cosine squared of x equals 3/4. Right, and then I'd square root both sides. So notice how I can solve these just like I would solve a normal algebraic equation. And I would end up with cosine of x equaling, if I take the square root of both these separately, cosine of x is going to equal √3/2, right, plus or minus. Okay, so then I can find the angles, right? Where does cosine of x equal √3/2? So I'm thinking in my head, on my unit circle, where's my x values? Positive √3/2. That's going to be a first quadrant answer of pi/6. And that's going to be a fourth quadrant answer of 11 pi/6. All right, so we'd be referencing our unit circle for that. Okay, so that's how we would go about doing that. You could do this one here on your own. Sine of 2x gives me 2 sine x cosine x equals 0. All right, because this is all multiplication and this is a 0, that's called the zero product property from Algebra 2. So we could split these up into two equations. All right, we don't know which one equals 0, so we're going to let them both equal 0. Okay, and then solve. All right, so where does sine x equal 0? Where does cosine x equal 0? Okay, so that would be another variation of using these identities. Same thing here. You could substitute for this. All right, okay, and then you have this extra cosine in the mix with it. All right, equals 0. We'd end up using a Pythagorean identity in there, and we would actually end up needing to factor this because a lot of it's going to look like this example here all the way up until this step, right? This step here, okay, would be the same down here, except you'd have that extra plus cosine. Okay, so we would have cosine 2 cosine squared of x plus cosine of x minus 1 equals 0. So now we're going to factor that, right, okay, into two binomials, setting them equal to 0, right? So that's why we were doing some of this stuff in lesson 1 with the factoring piece and simplifying, okay? That looks like it's about it for today. Okay, go ahead and give those a try. I did leave you hanging here with a couple of them. All right, see what you can get to or see what you can work through with those. All right, and then we'll pick up the pieces tomorrow. If you have extra time, please get into your Delta Math.